Hi, welcome back to Engineering 255 Statics. Today we're going to look at the last part of the chapter 10. The topic we're going to talk about is going to be the mass moment of inertia. Well, previously we were talking about moment of inertia of an area. And we also mentioned about the polar moment of inertia for the area. Now we are going to another different kind of a moment of inertia. Basically, this one is used if you wanted to find out the rotational dynamics. If you remember in the physics that you learn the energy of a rotation object is proportional to 1/2 I omega squared, where I is the mass moment of inertia, the omega is the rotational angular velocity. Over here, we are going to find out how do we find out the mass moment of inertia, and this is very similar to what you studied in the previous video. Simply just that when we do the integration in the moment of inertia for the area, we integrate with respect to the small area. Now we are looking at the small mass. So this will be a simple topic if you understand the previous materials. So the purpose of this study is that we are going to explain the concept of the mass moment inertia, briefly as the MMI. We're going to tell you how to determine an MMI for a composite body. So we're looking at some shape of the body that you can separate into the smaller one, and that's what we did in the previous video as well. And let's look at some application. Why do we care about this? So if you have a flywheel, like the picture shows you, it connect to another big piece. The flywheel will provide a uniform motion, and to make the cutting blade when it cut the materials, right? So the property of the flywheel is the focus that we wanted to know. How do we keep the flywheel rotating so this process will keep on running? And what will be the property that we can describe when you design any kind of a flywheel? What are the most important things that you need to care about when you design that? And that is actually related to the mass moment of inertia. The second example that we give you here is that let's say you have a fan, right? The fan blade depends on how many blade that you have. It's keep on rotating, and each one of the blade has a different kind of shape. And the torque or the moment to make it run is going to be depends on the angular speed, and it's going to be the rotation, how fast it rotate. It will start to increase, right? And then if you apply a moment, right? If you apply a moment, just like you apply a force to make things move forward, and it's going to accelerate. Similarly, for the rotation, you apply a torque, you will make the rotation start to increase the rotational speed. That is what we call the angular acceleration. Then with this acceleration alpha will be affected by the design of this blade. So as a matter of fact, this is also related to the mass moment of inertia. So let's think about the mass moment of inertia. If you have a body right here and it's rotating, and we wanted to know how easy or how hard this one will rotate. So when you calculate this I, it has like an idea, just like an inertia. And if you remember in the physics, inertia represents the resistance to the change of the motion. And over here is the change of the rotation. So the mass moment inertia kind of tells you is it how it will be resist to the rotational motion. And this MMI is the one that we're talking about. If you wanted to make it rotate and how the the torque is needed, and how much torque that will make it accelerate is in this equation here. The T represents the torque that the torque that you apply to this object. So how do you calculate torque? Torque is going to be the force times the distance. Okay, the distance from the rotating axis. And the I is the max moment of inertia. Alpha is going to be the angular acceleration, which is this one here. So again, the property is how does it resist to the rotation motion. And then this comes to how do we define that? How do we define the MMI, the mass moment of inertia? And here's the equation. If you look at the equation, it's very similar to the J. The J is equal to R squared dA. So we're looking at if you have a distance R away from the rotating axis, this R we just simply multiply with the small mass, and we sum it all together. That is going to be the total resistance to the state of the rotation. So here is the picture to show that if you have small mass on the body and you measure the distance away from the rotating axis, and that will be the R, you take the R squared times the M, and you can calculate that. Now, in terms of the unit, it's going to be different from the mass moment of inertia of the area, which is a meter to the force. Here we have R squared represent the meter square, the dm, m is the mass, which is going to be the kg. So your unit will be the kg times meter square. If you're using the US custom unit system, you use slug. Slug is the mass of the US unit system. Okay, and feet is going to be the length. This has the similar property like the moment of inertia of the area. You can also use the parallel axis theory. That means if you have a big mass, it's rotating, but it's not rotating any of the axis inside of the object, like the center of the mass of the object. You can rotate it about a point, and then you can use the parallel axis theory to find out if you are looking at, for example, this one here, the moment of inertia, the mass moment of inertia with respect to the z-axis. This is the z-axis, and your mass is right here. You can first find out the moment of inertia with respect to the center of the gravity here. Then you plus the d squared, which is the distance of this center of the gravity axis with respect to this rotating axis. And that d squared times the total mass is going to be the one that you add on top of your I with respect to the center of the mass. And this is the parallel axis theory. We can also use similar idea to find out the radius of the gyration. This gyration will be the total I divided by the mass and take a square root of that. So this one just tells you, what is this one measure? This one measure how spread the mass with respect to the axis that you are looking at. Now let's look at one of the example here. This example that you given with a volume like this one here, and it has a rho. This rho is the density. So the density of this volume is equal to 5 slug divided by feet cube. Slug is the mass, so density is the mass divided by volume. So this is the rho of this shape. The mass moment of the inertia of the body, we want to find out what the value is going to be with respect to the y-axis, which is this one here. So we wanted to see how easy to make this one to rotate, or how hard to make it rotate about this y-axis, and that property is what we call the IY. So we want to find that. So how do we use the equation? All right, so that's continuing from the previous problem and think of how we can solve this one. We're given with this curve right here is equal to y squared equal to x. So the height is equal to x squared, which is the parabolic equation like this one here. That's how this one is curved. Our goal is to try to find the I with respect to the y-axis, which is this axis here. So we're gonna start with this equation right here. So this is the moment of the mass moment of inertia for a solid disk. If you have a solid disk, then the I of y, this should be I of y, is equal to 1/2 of mr squared. M is the total mass, r is how big the disk is. And if this one is correct, then I can take the differentiation on both sides. Then we will have the Iy equal to 1/2 r squared dm. So the r is the size of the disk, so it's going to be a constant. The only thing will change is the mass. So the Diy is depends on the mass, which is this equation right here. This equation simply tell you about this one. Now, this one we replace with the x was because if you look at the circle like here, this is a solid disk. This r here is simply just the distance of the x. So we can replace this one as the x squared, and that will be giving you this equation. Now, we're going to replace the dm because in this figure, there's no way you can find out the information about the dm. And we have an equation to relate the density because this is one of the information was given in the problem. The density is equal to mass divided by the volume. And because of that, and we can take the differentiation on this part here, so we can rewrite this one as the rho v equal to m. Then we take a differentiation on both sides here, and we're going to use this is going to be a constant number, so we're going to say rho dv is equal to dm. Okay, so how big the volume is going to change how big of the mass is. Now, what is the volume of the small disk? The small disk volume is going to be the area of the disk times the thickness of this one here. So this part is going to be equal to the pi r squared, which is the circular area, times the dy, and that is our dv. And this r is actually the x, right? Again, this is the distance, which is the r, and that is actually equal to x. So we can rewrite the dm in terms of this equation right here. Is going to be equal to rho pi x squared dy. Now we're going to put this one in this equation right here, and then we can write our equation as this. Let me just clean this one up a little bit, and then we can write this one all together. Okay, so we can write this one as the 1/2 dm is equal to this whole thing, rho pi x squared, and multiply another x squared dy. That is equal to the diy. Okay, and we integrate on both sides, then you will have iy on the left hand side is equal to the integration of the right hand side. This should be like integration. Okay, and we are integrate of the y starting from 0 to y equal to 1 because y starting from this value to this height, which is 1 feet. And then we put everything here into this equation, which is 1/2 of the rho pi x to the fourth, right? X squared times x squared, x to the fourth dy. Now the next question is, we are integrating with respect to y, but we have an x to the fourth we have to rewrite this term in terms of the y. So how do we do that? Well, this one was given in the previous slide. The x is equal to y squared. So I'm going to replace this one to be the y squared to the fourth. And then give us y to the eighth. Now again, this one should be the big integral. This is going to be y equal to 0 and y equal to 1. And everything else just constant, we take it out. And then we integrate this y to the eighth dy. To integrate this one is equal to y of the 9 over 8. And we integrate this one from 0 to 1. And we multiply everything outside of this one here, which is 2 rho pi here. And you will get this equation right here. And that is how we find the final solution, and that is equal to 0.873 slug times v squared. All right, so I hope that you understand this process. The book has some other example, and I strongly recommend that you watch some of the example to understand this process. We're going to do some more example in the class. I'll see you in the class.